So let's consider differential equation of the form y prime equals the square of x minus y plus 1. Okay? If we were going to square that, multiply that by itself twice, you know, that if that prime, that y prime was in the left-hand side, if we just had the square of that expression, that's algebra, right? And you can see that by squaring that, you end up with x squared and y squared in terms x times y and x times y squared and y times x squared. So because the function y is appearing on the right-hand side with exponents different than 1, right, exponent 2, and because x multiplies y, well, this would be nonlinear. So as that right there with this formulation, this is considered non-linear. Non-linear in y. Okay, so the right-hand side is not linear in y. So, but that's not the end of the word. So we can actually define. We're going to define a new variable. We're going to say v is x minus y plus 1. So that v is the argument, right? That v is the argument of this function. This function is taking the square of something. So we're going to go with what happens if we set that argument to have a new name. And okay, and if we do this, then let's consider computing the derivative with respect to x, the derivative with respect to x in both sides. So we're differentiating v and we're differentiating x minus y plus 1. But remember that in all this, we're assuming that y is a function of x. So we are differentiating in both sides of this expression. Okay, we're differentiating both sides of this expression. We have derivative of v with respect to x on the left-hand side. On the right-hand side, we have derivative of x with respect to x, which is 1, minus derivative of y with respect to x, plus 0. Derivative of 1 constant with respect to x would be 0. So right off the bat, we see that this new variable satisfies that the derivative of this new variable is 1 minus the derivative of y, the original variable in the differential equation. So what we want is to be able to convert the original equation into a new differential equation. So since things from the previous step, we would say, you know what, we can actually move the derivative of y to the left-hand side, and we would have that the derivative of y is 1 minus the derivative of v. Okay, and with this information, we can rewrite the original differential equation. So we're going to say here that the original differential equation, let me call this equation, what will be a good name for this equation? I'm going to call this equation 1, okay? Equation 1 of the y prime equals to the square of that expression. So we're going to say, you know what, equation 1 becomes the following. So we have y prime is 1 minus the derivative of v, okay? And that is equal to v squared. So that was the whole point of making that, defining that new variable v, that we could express in the original equation, this right-hand side, we could express that in terms of a new variable. And so by doing this, we find we can move v to the other side. So 1 minus v squared equals the derivative of v. Or, equivalently, right, we could write the derivative on the left-hand side is 1 minus v squared. Now, is this linear? Is this linear? No, it's not linear. Because when we say it's linear, linear in what? So we're thinking linear in either the function or its derivative, or linear in both, right? And so the function here is v, the unknown of the ODE. The unknown is that function v, right? And in the right-hand side, v appears with an exponent of 2, is square. So that is not linear, right? So it's not linear. However, we can use a technique to take care of this, right? Because we're interested on v as a function of x. So we could do what? Separation of variables, right? Separable equations. This is not linear, so we wouldn't use integrating factor, but we can use separation of variables. So we could write, say, this implies we could write the expression in terms of v here on the left-hand side, and then on the right-hand side, we would write the expression in terms of x. Now, let me rewrite this left-hand side as that is actually a difference of squares. So you could write that as 1 minus v in the denominator, quantity 1 minus v multiplied by quantity 1 plus v. And the right-hand side is still looking like dx. Now, does this look familiar? Looks familiar. How about the students in the WebEx space? Does this look familiar? Oh.
Oh yes, looks just like one of the problems we worked last Friday.
What?
Or
Don't
not
give
Friday,
away.
Tuesday.
Hold on a second. Okay, so that must be Anthony, and I think the other student that identified himself earlier, Mr. Jones, they were both part of a group discussion yesterday and during office hours, and this looks similar. However, it's not exactly the same expression of one of the exercises that were discussed yesterday. Okay, it is true that it was a difference of squares and that one of the squares was 1, but it's not quite the same because what we have here in the denominator is 1 minus v squared. I believe that problem, that exercise, was actually v squared minus 1. Okay, but you would take care of this exactly in the same manner as for that previous problem. So you would have to use partial fractions. Okay, so partial fractions on the left-hand side, and then you would find that the right-hand side is easy, right? But so the left-hand side is what's a handful, and then you end up with 1/2 natural log of the absolute value of v plus 1 over v minus 1. So the denominator is v minus 1. And on the right-hand side, you're integrating with respect to x, you end up with x plus some constant. I lost track of how many c's I have, so I'm going to say C sub 5 there for the sake of, so, and so doing a little more of, now we're trying to solve this for, V, right? So we multiply by 2, and this here becomes 2x plus 2 times c sub 5, the still natural log of this absolute value. And then we exponentiate. So we haven't really said here what are the limits of integration here, but well, we exponentiate. So we have absolute value on the left-hand side, and here we have e to the 2x, and we can consider e to the 2 c sub 5. We can consider this a whole new variable. Let's say that variable is called d. Okay. So on the left-hand side, we have this ratio v plus 1 over v minus 1. And see, here's probably where we need a note. So if v is bigger than 1, okay, then we can get rid of that absolute value. Both of those terms would be positive, and we have v plus 1 over v minus 1 equals d times e to the 2x. And since we're interested in solving for v, we have to cross multiply, right? Multiply in both sides by v minus 1. Multiply this by v minus 1. So we have v plus 1 equals d e to the 2x v minus d e to the 2x. And so therefore here we have v minus d e to the 2x v equals minus 1 minus d e to the 2x. We're solving for v, right? So this looks like v multiplying 1 minus d e to the 2x. Which implies that v is the expression minus divided by 1 minus d e to the 2x. This looks almost good. Almost, it is almost where we need it to be, but not quite, right? Because the last step, the last thing we have to do is to unsubstitute. And substitute. What does that mean? It means that you go back to what was v, all right? So v is x minus y plus 1. Okay, v is x minus y plus 1. So let's go ahead and write that. So x minus y plus 1 equals this expression. And we would need to solve that expression for y. Right? The original differential equation was in terms of y prime, and it involved y and x. So at this step, you can see that y only appears on the left-hand side. The right-hand side is in terms of x, so it's not that difficult to solve for y. Okay, so I'm going to leave that. Step for u, and